Welcome back, chat. Today we are going to jump in. We are continuing on really briefly. The other day we started talking about chapter 4, it's population ecology, and then I didn't write it here, but in 4.1 it's in population dynamics. And remember the shortcut for population because we're going to write about 1 billion times, just pop. Okay, so remind me, what are dynamics? We talked about statics and dynamics. Static means something still. Dynamic means changing or moving. Okay, now when we're looking at population characteristics, doesn't matter if we're looking at human beings or like wild animals or fishes or bacteria, irrelevant. What we're going to be able to do is look at a given population and discuss some of the characteristics of that population, and it turns out that they're pretty easy to classify. However, the first one, rather than me just telling you something, I would be much more interested in looking at real world stuff, especially real world to us here, to make sense of it. So, the first one, did we write any words?
We put population density.
Awesome, and we did not define it, is that correct? Yeah. Okay, so population density. And you should already have this written down. Killing me, Fred. All right. So I'm going to make you guys help me with something here in a minute. But we're looking at population density. And did we define this?
No.
Okay. So we're going to start getting a little bit of mathy looking stuff for a minute. Which, Bam Bam, if you don't know this, like, I was a math teacher for years and years and years. I still teach some math. But math and science is my thing. Biology is one of my weaker sciences, just so you guys are aware. Like, fully transparent. But the cool thing about that is it means that like I've seen everything here and I know this stuff, but it's like me relearning it again, and it's a pretty cool thing. Okay, so population density, easy. We're just going to say that by definition is the number of organisms. So it doesn't matter if we're talking people or whatever the case is. The number of organisms per unit area. All right. Number of organisms per unit area. Now, when we're looking at this, when you see per, this word, and we're going to say if it's gray, put the pencil away, as in don't write it. So that looks kind of white to me. But that color will just be my pointing at stuff. What does per mean when you see it? Where would you see this in regular, like, everyday usage? The word per. Per minute. So, like, if I said texts per minute, what does that mean, like, as a calculation? Is it adding, subtracting, dividing, multiplying?
Oh, it means every.
So, one of the two. I don't think it's multiply or add. Check it out. Outside on the road, it's 30 what? The speed limit, 30 miles per hour. So that means if you were to go for 1 full hour at that speed, how far would you go? 30 miles. So that's 30 miles divided by 1 hour is what that really says. Now, looking at it, why I'm making us think about that is we're going to give ourselves this nice idea here. I'm going to say a nice formula, the population density. When we're looking at this and how we calculate it, it's really and truly just equal to the number of organisms. And then instead of using the word per, and I'm going to make this look mathy, what did we decide it was? Divided by area. Okay. Now, here in Dutch, compared to other places in the world, we have a really low population density. And we talked briefly at least about cities the other day, and we talked about if you wanted to go on a walk and not see people in LA or Seattle, you wouldn't be able to, right? Because they have different population densities. Are you interested in seeing some human population densities? Yeah. Okay. We are going to do and calculate out population density, but we're going to do population density of something that's not just made up and fake. You guys are going to help me. We're going to check out a video that I took yesterday. Cool. So, I'm going to go back and forth from a survey that I took yesterday. We're going to look at just that section of the river. I'm not going to show the video here if you're watching this again. So, In that video, we just saw in this region there were how many fish? We counted 150. Now, those are salmon. Do you know what type of salmon are over there right now? Pinks are gone. Pinks are dead. These are silver salmon. Okay. Coho, you may see them referred to. Coho. All right. So we just counted 150. What I want to know is their population density. Now, if we look at this, we're going to see something that I hope will make sense. Let's just carry out this calculation. So if we're trying to find the population density for our river over here, just that little stretch. So pop density. How many fish do we count? So 150 coho, and I'll say silvers. I should have wrote coho because that's shorter. Over, what was the area that we had? 120 square meters. Now, this unit may not seem super meaningful, and I would agree with you. This doesn't really do justice to what's happening there. If you open your desk, most of you, or some of you at least, should have a calculator. Will somebody grab out a calculator? And actually, we could probably do it. It's 1.25 is what this is going to be. Pretty sure of it. Now, I'll wait till somebody verifies. 1.25? 150 over 120? Okay. Now, right now, this doesn't really mean a ton because looking at that over 120 square meters, that can be hard to think about. But if we simplify this out, we get approximately 1.25 coho or silvers, whatever you want to word it, per every square meter. Now, there's an issue with this that I think is pretty obvious. Do you think it's possible that I could have drawn a little meter by meter square there and saw 0 fish? You don't think so? Like, if I draw a 1 square meter, and we'll go back to the end of this video. Like, check it out. We'll come up here. Here's this video. So check it out. Here I am. And we'll just go a little step forward. Okay, so check it out. If I were to draw this square meter, how many fish do you see in here? So there's really 0. Do you see an issue with the way that we talk about population density then? Because what our number just told us is that for every square meter, we should find how many fish? 1.25. Why doesn't this work?
Because some are in one place.
Yeah, but notice this isn't real. And specifically, I'm going to say this isn't a great representation, which means it's good to know, like we can tell how many fish are there in that big area, but it doesn't really tell us a ton about the population other than the number of fish. This isn't a great realistic statement. Now, I want to make sure that we hit that with a grain of salt. There's nothing that's untrue about what we just said. That is the population density that we just calculated. However, it's not very meaningful. So, we have looked at this. Population density, 1.25 silver per square meter, means that we should be able to go and be able to get them. Unfortunately, as somebody just brought up, the way that they're organized doesn't really align with this. If they were distributed equally throughout the river, this is what you would find. Our second characteristic, instead of just looking at population density, maybe there's a more meaningful way that we can talk about these things. So, moving forward, we're going to give ourselves another characteristic, and we're going to talk about spatial distribution. Okay, spatial distribution is a much more, not even more, an equally important part of this. It'll make this number make so much more sense. Commonly, you'll see this as instead referred to by the single word dispersion. How are these populations, or these specific fish in our example, how are they dispersed throughout the river? Okay, now when we look at this, dispersion as an easy definition, we'll just say the spacing pattern. The spacing pattern. Now, depending on the population, the spacing pattern in an area. Sorry. This will vary pretty wildly depending on the type of population that we have. The way that fish live is exactly the same as the way that bears live, right? No, it's not. Don't just agree with me. Okay, so looking at this, there are three main patterns that we're going to deal with. And let's check them out. Three main patterns. I don't know why that P is a capital, but that's okay. Okay. For these, you do not have to have the same number of dots that I do. The first type of pattern that we might get for dispersion, and I'm just going to draw three right here with pictures just so you know. The first one is a uniform dispersion. And all I'm going to do is I'm just going to draw a box underneath of it. Okay. If a dispersion is uniform, anybody have any idea what that means? Okay. And I'm all right with that. Uniform, as we look at it, if we have a uniform distribution, it's what you would expect to get out of our population density. I'm going to use bigger dots. Uniform distribution looks like this. Where they're all essentially equally spaced all the way through. When we click back over, and I'm going to let you guys get this, it's just equally spaced. Do we have uniform dispersion here? No. So, means that maybe we don't have it. Can you think of an animal that maybe is like this? And it can be tough. So humans, not as much. But I think we do have them in Alaska.
What's that?
So if it's uniformly dispersed like this, do they run in packs or groups? Careful, these aren't in groups, are they? They're just individuals separated. So it can't be wolves, it's not going to be fish. Humans live in groups as well. Birds, they go in flocks.
How about bears?
Ooh.
No.
Bears don't run in packs, do they?
They're like far away from each other.
They're far away from each other, and that makes sense that bears are far away from each other because they all compete for resources, right?
Meerkats.
So yeah, colonies. But I think bears is a good example. And actually, I have black bears on mine, but that's okay. Bears is fine. Okay, beyond our uniform distribution, another alternative that shows up naturally all over the place is what we call a clumped or clustered. Now, a clump or cluster is going to have all those same populations, but maybe there's, instead of being equally spaced everywhere, they run like this. Can you give me an example of a clumped or clustered population? Hey, the salmon that we just looked at, those are certainly clustered, right? Now, why? Why would the salmon over there be all huddled together? Like we see this gigantic group right here. Why are these guys all clustered together?
So that when a bird attacks them, it only attacks like one.
Yeah, if something were to attack these fish,
Yeah, like
there's safety in numbers, right? Like they don't have to worry about it. An eagle's only going to take one of them. Cool. Okay, can you think of another population that might do this? We're thinking herd animals at this point.
sheep.
Sheep would do it. Elephants would do this as well. Caribou do this. I'm going to write sheep. I like that one. So salmon, sheep, there's a bunch of them that do it. Okay, humans, it turns out, pretty much do this. Like if you look at how people live, in the suburbs you might find something like this because everybody has their own house and their own yard. But if you go to the city when you have apartments, this is what it's going to start looking like. Okay, the last one is random or chaotic. I like calling it random. Okay, this one I'm going to put dots, but they're not going to be like I'm just placing these at random. Some of them are really close together. Some of them are super far apart. A random spacing. Now this one's going to be harder to identify just because of where we live. Can you guys think of an animal that has a random dispersion like this? Ants, careful, ants all live like really tightly packed, right? So ants have a colony. I would say ants are more clumped like this if we look at it.
How about that squirrel?
Ground squirrels? I'm fine with ground squirrels. The example that I use is from where I'm from, deer. Deer all are chaotic. Sometimes you'll see groups of 10. Sometimes you'll see one at a time. Like, it just varies. Ground squirrel's a better answer here, for sure. Now, every single one of these applies to every population. As we think about this, the main driving factor in what makes animals clump up like this, there's several of them, obviously, but we're going to say access to food and water. To food and water. And then I can think of one more. This is a pretty big driving force to how populations are spaced, right? Bears are spaced out because they're food. Access to food and water, this is a primary cause. Okay, there are, however, some secondary causes that may play a bigger role. The salmon aren't spaced like this because they want food and water. The salmon are spaced like this, what? Protection from predators. So I'll say protection might be a second follow-up. Okay, turns out maybe there's a little bit more to the salmon than just the protection that they're after, but it's a big driving force.
What's that reproduce or the eggs? When they
Protecting something.
yeah, like when they're about to lay eggs and the male.
Spawning. So they're spawning. If we look, and I'm sure we could find it, I'm not going to make us just look at this video. If we go up a little bit of the river, though, we'll see it. So these fish, just looking at it, I think this is a female. If that's not a female, it's a really small male, then this is a female. This is noticeably a bigger fish. Who do you think? What is that? That's a male. So if we watch just what he's doing, notice how he's just kind of sitting here watching. That is a female, I'm sure of it. He is watching to see if she lays her eggs. These guys over here just got over there. They're not, like, these guys are ready to lay their eggs, they're ready to do their thing. This whole group, I would guess if we zoomed in, you have one female and several males around because they're waiting for her to lay her eggs, and then they all run forward and they fertilize the eggs. So they don't have, like, physical relations. She lays eggs, and then they lay their milt to fertilize it. And you might have 2 or 3 male fish come in and milt to try to fertilize the eggs because they're there. Like, why not? Okay. Looking at it, once they move into the spawning phase and they're actually like in the active reproduction going on, what sort of distribution do we have here? I'd say this is more chaotic, right? They're not as clumped together. It's randomness that we see. It's definitely not uniform. But even within one population, depending on what they're doing, it can change as well, right? Like, if all the bears in Kodiak happen to be going to get salmon, they're all, like, there's enough salmon to go around. They move from this uniform distribution and they come into this cluster or this clump. Like, it depends on what their end goal is. Okay. Feel okay with these ideas? Sweet. So I don't know for sure, was it more interesting when we made it the real river, or is that not something I should do next year? Okay. All right. Couple more that are super chill and really fast to hit. Next, we're going to look at population ranges. Population ranges. So remember, we're doing all these things to talk about how a population is organized, like the whole population. Where in the world do humans live? What range of environments? Do they live in temperate zones? Yeah. Do they live in tropical zones? They do. Do they live in polar regions? Yes. Do humans occupy every biome on the planet? Oh, not quite. Why? Hey, we don't live in the water. Okay, so when we're looking at this, this is an oddly surprising thing when you write it, but when you think about it, maybe not as much. We're going to make a big claim. No population on the planet, not a single one, inhabits all habitats. Now, I think it's safe to say that human beings are like the most diversified geographically out of all life on our planet, but no population inhabits all of them. Okay, looking at this. Some species, I'm not going to rate much. There are species that exist only on a small island. Like, The only members of that population are there. The Galapagos Islands are a good example of that, where Darwin went. There's tortoises that are Galapagos tortoises that don't live anywhere else in the world. They're just on that island. There are axolotls, which you guys know what an axolotl is? Like the cute little lizard things. There's axolotls that only live in one specific lake in Mexico. Some of them are really, really, really refined in their range. There's animals, however, that also go across multiple continents or oceans. For example, sharks. Sharks live everywhere, right? Great whites you'll find on the East Coast. You'll find them on the West Coast. You'll find them in Australia and Asia and Europe. You'll find great white sharks everywhere. Whales are the same. You will see whale populations. Blue whales will live all over the planet in a variety of different oceans. Okay, looking at it. Biotic and abiotic factors play a huge role in this. So specifically, weather conditions are a huge driving force in your range. Monkeys don't live where it's... Okay, that's not true. Let me rephrase this. Mountain gorillas don't live where it's snowy. I was going to say monkeys don't live where it's snowy, but that's not true. Monkeys do live in snow. Like, it's crazy. Cool. All right. So we have seen 3 characteristics at this time that we use to discuss populations. Give me one of them. 3 population characteristics that we've discussed so far. Spatial distribution. There's 3 patterns. Give me one. Uniform distribution. Okay, give me another. One more time. Clumped or, Fred? Random. Okay, so the way that they're distributed or dispersed, that's one of the characteristics. Give me another characteristic we talked about already. How packed in are they is like the leading... Density. Population density is another characteristic. The last one that we wrote down only wrote a couple things about it. The range. Okay, last one that we can use to talk about a population, and there's so little to write here. We gonna talk about population limiting factors. So population limiting factors. And that should be a bullet point, sorry. Population limiting factors. All right, we're going to take a quick brain break because I've been talking for a long time. Do you want to do a little math exercise? No? Okay, you guys have math next hour, huh? Okay. I'm going to let you guys get your phones real quick if you need them. You're going to find me a fun fact. Find me a fun fact related to biology. No Snap, no Insta, don't get it from TikTok. Cool. Go grab your phone, RJ. Find me a fun fact. Something about biology. Preferably related to ecology, but I'm okay if it's not. Quick fun fact. Don't text people in other classes. I'll give you a minute. So, population limiting factors. Right now, do you know how many people there are on Earth? 8 point something billion. Okay, 100 years ago, there were like 5 billion or 4 billion. Like, it's growing faster and faster and faster and faster. In 100 years, are we going to have 1 trillion people?
Most likely.
So,
I don't think so.
why don't you think so?
Because countries will I don't know, overpopulation.
So right now, so maybe countries would step in, and they would have to, I'll tell you. War might have something to do with it, but there's a scarier reason. Maybe not scarier, but equally scary.
The sun.
So not so much the sun. Right now, are there people on this planet who don't get enough food to eat?
Oh yeah.
And we only have 8 billion people. If we had 20 billion people, what do you think is going to happen with a lot of them?
Less resources.
Less resources means they're going to starve. They're going to die. Okay, there are things that limit populations naturally that aren't as scary as like global famine. We'll jump in right here tomorrow. All right, later Raiders.